Hello, how are you?
I'm good, thank you.
And we're live right now.
Oh, wow, cool.
One sec. There we go. So, hi everyone. Thanks for joining us today. We have a whiteboard session with Alexey working on TurboGeth. And joining us is Dani, Michael, Misha, and Eugene, who would be asking all kind of questions that they have after they watched the recent video by Alexey about the TurboGeth. So I'm gonna let you guys kick it off and just don't mind me from now on.
Awesome. Okay, so I'll get started. So Alexey, I know we talked about how you've been researching this for Ethereum for the past 3 years, and you found really some proposals for improvement regarding constructing state in a better way in order to avoid having to deal with issues like state rent or staking for said state rent later on the line, just getting the design right. And so we talked about kind of learning from those best practices. So I wanted maybe if you could tell us about those best practices for the group, or like what were your findings, and that can be a starting point for us here.
Yeah, so thank you. Yeah, there was a, can you hear me okay? Yeah. I'm just kind of muffled, you know? Okay, can you hear me?
Can everyone else hear Alexey?
Yep, sound good to me.
Okay, so because I just come across muffled to myself. Anyway, so the conversation I guess started when we were thinking about the state rent, and a lot of people probably are aware that we had the state rent project in Ethereum. And the reason why it started is because there was a realization that the state is very large, and it basically the size of the state was creating a lot of the issues, for example, synchronizations and processing. And so it looked like a very kind of crucial, very urgent problem. And nobody really knew exactly how big the state was. And that was actually interesting because depending on how you store it, the number would be different. So if somebody asked at that moment, but how big is it? Like, what we're talking about? And some people say, well, it's 100 gigabytes. Some other people say, no, it's 60 gigabytes. So it was already the first sign of that we don't really, this is not very well defined. So, and in the TurboGeth, very recently, we have experimenting with different ways of laying down the state. And until recently, we had a representation which currently would be, where we state currently would be 50 gigabytes, which was already quite a kind of good achievement. But then we found another representation which is as efficient to access as that one, but basically is 10 gigabyte. So, and then made me thinking that if that is possible, then a lot of the worries that we had back then in 2018 when we kickstarted the state rent project were actually not as urgent as we thought they were, and we can address them in a much better way instead of we do still have time to think about those things better, and whether the state rent is actually does have to be coming right now, or could it come a bit later, because it does come, the state rent does come with a very hefty price tag if you introduce it on a live system. Of course, if you design a system from scratch, and maybe you can do that much easier, but trying to put a state rent on Ethereum where there has never been a state rent is actually quite hard, and it's taxing. So yeah, that's basically what we were talking about before.
Right.
Misha, do you want to ask questions that you had?
Yes, so actually the most relevant part of the presentation for us was the flat state.
The flat state,
so,
okay.
Yeah, so this is a very relevant problem for us, especially with WASM execution. So in our case, contract execution is very fast because of compiling into native code, but storage access is still really expensive.
Mm-hmm.
So we are very interested in optimizing it.
Okay.
Yeah.
Well, to be fair, actually, I don't know if you've seen that on Friday there was the, I mean, there was another talk on Friday, at least online, but there was another one which is called EVM 384, which is basically, this is a project which also has a long story. And essentially the moral of the story is that the EVM, you can actually make EVM interpreter very efficient. I mean, the perception of people had before that EVM is a sort of EVM interpreter has to be super slow, actually is not really justified, because you can write very efficient interpreters, and actually there are already efficient ones. And in this particular talk, they demonstrated that for certain things, you know, if you had certain operations added to the EVM, it actually becomes more efficient than WebAssembly. And simply for the fact, because EVM has the long word operations, like 256, and this proposals, for example, introducing 384-bit operations, and WebAssembly has essentially 64-bit, and it has to assemble all their more complex operations out of 64-bit operations. So it's not fair to say that, you know, WebAssembly is by definition faster than EVM. It all depends on your interpreter. But coming back to the state problem, yeah, definitely. So the flat state is exactly where the flat representation state is exactly where the TurboGeth project started, from the observation that when we do state access in the traditional layout, when we represent the state as a radix tree, essentially. So I can start drawing if you want. So some people kind of know it as the Patricia-Merkle tree, but actually there is much more standard definition of this radix tree that usually if you had like a job interview, sometimes they ask you a question, how would you like if you had a dictionary, if you wanted to take a dictionary and put it into a data structure in your program, what would be the very efficient way of representing a dictionary? In the dictionary, essentially, you have to look for whether the word exists or not, and if it does exist, you need to, let's say, find either a definition or translation to a different language. So usually the way, can I? Oh, why is it not? Oh, because I don't have a pen. So usually the dictionary, so the correct answer to this interview question is the radix tree, where you essentially build for, so the radix tree consists of multiple levels, and at each level you can basically have, let's say that we have only 6 letters in the alphabet. And so the first level is that all the words that start with letter A, they go in this way, and all the words starting with letter B go this way, and so forth, right? And then sort of like, then the second letter, then the next level is the second letter of the word in a dictionary. Let's say that if we have a word apple, then it of course will start with letter P, and there is no letter, let's say that there's no word with starting with 2 letters A, like there's no AA. There's like AB, for example. So that thing would start with the B. So we have words starting with AB, like abacus, and then we have the word starting with AC, which is like, what is the starting with something? I don't know. There definitely exists, or something like that, right? And so you get the idea. On the second level, you have all the kind of letters here and so forth. And then on the third level, you get the, what is the third letter in the word? So abacus would have A again, and so forth. And sort of Abba, for example, if Abba was in a dictionary, then it will be here, and so forth. In the end, you get all through the levels, and somewhere in the end, you will get either the definition of the word or the translation. So here you get, so that's a leaf of the tree, definition of translation. And so basically, if you're basically building a dictionary in a job interview, this is what you have to say, you know, the radix tree. And so that's the similar idea to what the Patricia-Merkle tree is, or any other kind of radix tree. But so in order to map this problem to the dictionary question, is that in Ethereum, for example, imagine that instead of the words in a dictionary, you have addresses of the accounts, right? And that's why if the first, and here, essentially, in the first level, instead of the first letter of the word, it basically, you look at first 4 bits of the address or something. And so there's only 16 variations of the first 40 bits. So you know that in the first level, there will be at most 16 elements. And then in the second level, at most 16 elements and so forth. And it goes all the way down to a certain level where there's no more, you know, as you can imagine that with the dictionary, for example, at some point you don't really have a lot of branching anymore, because, for example, if you take the same example of abacus, after you've done A, B, A, ABBA, there is no many words that actually start with the AB, like maybe AB, ABA, or whatever. So imagine that there's no other words which starts with ABA, and then so in this case, your abacus could actually be straight here. So let's sort of like erase this. And so let's imagine that there is no other words that start with ABA. So what we do, let's in Ethereum, then we say we put the kus in here as like some sort of special element, and then we map it to the definition or something like that. And the reason why we could do that is because it's essentially like there's no other words with such prefix. And this is you know, the way to kind of compress this is how you can compress the tree. Yeah, in Ethereum, essentially the definition, instead of definition, you will get a balanced nonce and something like this. And of course, it's not only in Ethereum. And that's basically the structure. And it's all good, but there are a couple of nuances to it. When Ethereum had one of the audits, the guy who did the audit, Andrew Miller from Least Authority, or at least he was at Least Authority, he basically noticed one thing, is that it is possible if you just use simply the addresses of the accounts as the words in such dictionary, then it's pretty easy to construct very kind of deep. So because we're not really like here, it's not a dictionary, it's the the addresses, and you can generate the new addresses very, very easily. So what you can do is that you construct the structure, which is super, super deep. And you can see how you can do that. What you need to do is that you need to find 2 addresses which have basically really long prefixes, 2 different addresses, but they have very long common prefix. For example, if you manage to find 2 addresses for which actually it's not very hard, because basically you can just say FFF, FFF, and then on the very end you get basically let's say F. So because the address is 20 byte long, so the depth of that thing is going to be 40 nibbles, what they call nibbles, and then you generate another one which is going to be exactly the same, but with the E in the end or something like this. So yeah, and then you're going to have a very deep tree, and there could be other things like, oh, so he was actually suggesting to do something like the spine structure. So it's not just you do it on the very bottom level, but you branch it on every single level. So you're creating some kind of spine structure like this. On every single level, you do this kind of branching. So basically, by doing this, you're creating a very deep structure, like it's 40 levels deep, and then basically the reason why, usually you say, okay, on what? Like, okay, 40 levels deep, and what's the problem? Like, okay, that's fine. It becomes a problem precisely when you start thinking how you store this in the database. And this is where actually get.
Can I interrupt you for a moment?
Yeah, sure.
So I just want to summarize kind of my high-level understanding. So the goal of this tree is, the ultimate goal we have is to have a state root.
No,
And,
not. It's one of the goals, but it's not actually the only goal.
So, okay, so what are the goals of actually this building this tree?
So the goal, from my point of view, the most important goal of this tree is to be able to add things easily and find things easily. Like it's essentially a representation of a sorted map. It doesn't have to be sorted. It could be kind of just a map or something like this. But you need to do it in such a way that you can actually calculate some kind of commitment to this entire map. And it happens to be that people decided that the commitment to this entire map is going to be a Merkle tree of certain construction. But the problem of computing the hash root in a specific way wasn't there in the beginning. It has been constructed. The original problem was to be able to have a data structure where you can put stuff in and you can get stuff out, like a mapping.
Sort of. So what I mean is that if we don't have state root, it doesn't have to be part of the protocol. It could be any key value storage.
Correct, yes. So yeah, if you need to, where do we come to the state root thing? We come to the state root because, so when we say, okay, we need to make sure that everybody has the same mapping, right, in the memory or somewhere in the database. How do we ensure that? Well, first of all, if you look at what Bitcoin does, let's step back from Ethereum, because in Bitcoin you can imagine that they have the same kind of structure, but it does not explicitly specified in the protocol, because in Bitcoin there is also a state which is a set of unspent UTXOs, right? And you need to have a state in order to be able to verify whether a certain transaction is valid or not. So it's the same kind of thing. But the difference is that in Bitcoin, they don't construct commitment to the state and they don't put them in a header. So what they do is that they assume that everybody is having the same code, or code does the same thing without bugs. So that if they run all the blocks, they will arrive to the same state. They assuming that everybody could do that. And if somebody doesn't do that, it means that they're incorrect, then they sometimes can do wrong things. In Ethereum, essentially for lots of reasons, the designers decided that, okay, we don't just assume that everybody has the same mapping, but we want to somehow compare these mappings. I mean, of course, Merkle trees were known for a long time for such purposes. Like if you take the products like Cassandra, for example, it uses Merkle trees all the time to reconcile the replicas. So if you have two replicas and then data missing in one replica, they use Merkle tree to quickly find out, what is missing and just reconcile it. So they call it repair. So here, exactly the same idea. Okay, let's have a Merkle tree, and then we basically going to have a way to reconcile the replicas. Because basically it's a replicated database, okay, that's in the replicated state. So, and somebody chose this particular form of Merkle tree for the task.
Yes, so Ethereum, as I understand, uses this Radix tree with hashes of keys for keys to make it balanced.
Correct, yes.
Correct. I know that's some other projects have different ways of building the tree, such as like balanced binary search tree, ABL.
Correct. Yes, the notable example is Cosmos, right?
Mm-hmm.
Yeah, I've looked at that structure as well. So yeah, that works too.
Have you looked into trade-offs between them at all?
Yes, I did. So the trade-off is this. So one of the main properties, one of the main differences. Can I create a new page here? Is it like this plus button, right?
Yeah, but you can also like scroll down with, you have the controls on the right panel. You can just click on this cross there and scroll it down, or you can create you can click plus too.
pan, you mean the pan thing? Okay, fine. Yeah, so essentially the trade-off are quite interesting. So the trade-offs are in the balance tree. Let's say it's IVL tree, or it could be weight balance tree or whatever, red black tree. So the AVL tree are probably the best ones because they have a much better bound on the depth. So what happens in the balanced trees is that if you take one tree, so they basically binary, and you imagine that this is like some kind of algebra, right? So in this algebra, your trees are your elements, and then you get some operators that operate on these trees. So for example, one type of operator is that when you want to add a key value pair, which is basically adding some sort of key and then value at the end. So that's one operator. Another operator, for example, is deleting the node. So another operator is removing certain key value pair, and so forth. So there's two main operators. You add something, you delete something. So the main property of the radix tree is that all the operators are, they commute with each other. It's this particular kind of in this particular algebra, these operators are commutative. So you can basically add elements in any order, and then or remove them in any order. In the end, it doesn't matter in which order you've done it. What really matters, one correction: the additions are commutative, but the and deletions, but they do not commute between each other. So basically, additions commute with additions, deletions commute with additions, but the additions and deletions obviously do not commute. So you have to know in which order to apply them. But for the balance tree, it's not the case. In the balance tree, these operators are not commutative. So it does matter in which order you add them. So essentially, if you have two elements, you add them, let's say A and B, and take the balance tree, you add A first and B next. You can have a different tree than if you actually add B first and then A next. So that is a bit of a challenge. And if you need this property, if you do need the property of commutativity, then you have to solve it somehow. You need to, I mean, there are solutions to that, but that's the main cons, I mean, the disadvantage of the balance tree. But there is advantage, of course. In the balance tree, you don't have to do these extra hashing to produce the balance, because the tree balances itself, and it simplifies quite a lot of things, I would say. For example, because you have this hashing stuff for some implementations, initially we also had it, but now we don't. You've got to have these pre-images, which are quite annoying. When you look at the tree and it's hashed, and you have to always, like, let's say, basically, if you go back to this tree, if you imagine that these these letters, like these paths in the tree, are not actual addresses but the hashes of addresses, and you somehow found one of these hashes, how do you recover what the address was? Well, it's not really possible without really knowing, without having another database which will map the hashes to the addresses, which is a bit of a trouble. Anyway, so I think the main thing about the balance trees, but the main thing I like about balance trees is that you don't need to do this extra step. But as we say, it's a bit of a, it's a trade-off.
Yeah, so then if we're implementing a client, so the client would store, for this try structure, it would store a mapping from a hash of try node to the node object, essentially.
Well, this is how the yellow paper tells you to do so, but that's not how you should do it.
Well, yeah, let's start with this naive implementation.
Okay.
And then that would be, for that, it would be using some kind of key value storage.
Yeah. That's what everybody essentially is doing. They are So if you go back to that structure, or I don't know, it doesn't matter which structure it is. It could be this one. If I just let's make it a oh gosh, what is it? I'm just getting confused. Let me see. Let me erase this thing and this thing. Okay. Okay. Let me just have a little tree here. Okay. 3 levels will be enough. Okay. Right. So the way I usually think about this is that imagine that you have the nodes are pointing to each other. They got pointers, and each pointer is I draw it as an arrow here. So usually when you have those structures in memory, you basically have this element on the top. Okay, so how do you actually point to something here? Is there a way to point? Like
there is.
We can see your cursor.
My cursor. Where? Well, I don't have a cursor as an iPad because yes, I don't. That's why I chose iPad because it's easier to draw, and then I don't have a cursor. Anyway, it doesn't matter. So I'm just gonna say, so even in this top element where I drew the 2 arrows from it, imagine if you store this structure in memory, not in a database, what it would mean is that this top element would have 2 pointers, right? And the pointers usually, I mean, if you have a 64-bit architecture, the pointer is essentially a number, which is 8-byte number, which has the address, the memory address of the thing that you're pointing to, so that you can go there and look. It's very similar how these naive, would say, implementations do it, but instead of the pointer being 8-byte memory address, the pointer is, in the case of Ethereum, 32-byte hash. And in order to dereference this pointer, in order to find the things that it points to, in the case of our memory, we simply need to ask what is inside this memory address. In the case of the database representation, dereferencing the pointer means looking up that record using this hash as the key. So it's basically the same process. So that's why if you establish this connection, then you can basically think about this as the pointers in memory, and then you can very easily reason about what happens when you access things. And you can obviously see that the depth now matters, because if you always start your search from the root, which you basically have over time, and you need to find something, the deeper it sits, the more hops through the pointers, the more dereferencing operations you need to perform. And then if you remember that in a database, dereferencing means doing a lookup, then you realize, okay, if I go 8 levels deep, I do 8 lookups. If I go 40 levels deep, I do 40 lookups. And another feature of that is that you cannot parallelize it, because they are data dependent. You cannot hop, let's say in this picture, you cannot hop straight from the top element to the second level. You have to first go to the first level, then to the second level. So you can't skip the levels because you need to find this. It's like a a quest. You need to find the next pointer, and then the next pointer, and the next pointer, and that's why the depth really matters. And that's why this security audit I was talking about, that's why it was a problem if somebody could create those spines, as I was pointing out. Those, okay, where's this thing again? Oh no, it's the wrong button, sorry. Yeah, the spines that I was drawing here, right? You see the spine? No, actually, no. Anyway, so you can't see the spines because you somehow moved this thing around. I don't know. But the spines that I was drawing, yeah, the spines, yeah, on the right. So the problem with those spines, if you manage to construct them, then you force the tree to be very deep, and then all your queries inside the area of this tree are going to be super slow. So you can specifically, like, if you don't like a certain contract, if you want that contract to become slow, you create spines around this contract by basically sending, one way, a transaction with one way to those addresses, and you don't even need to do any kind of address mining. You just do that. And of course, if you now hash everything with the SHA whatever 256 before you put in a tree, it's still possible, but it's much more resource intensive. So you need to buy some SHA-3 ASICs to be able to pull that off. I mean, you could still probably go a few levels deep, but I mean, it's not that potent anymore. And yeah, that's actually the good point, is that this pre-hashing before putting it into the tree is not a perfect protection against these balancing attacks, whereas the self-balancing trees are pretty much the best protection you can get theoretically. So it's theoretically the best protection.
Yeah, so let's start with the naive implementation and then try to optimize it.
Okay, let's do that.
So, in any case, we always have to compute state root for each block, correct?
Not correct. Not in any case, because so what you can see now happening in Ethereum is that a long time ago, I don't know which year was that, 2016 or 2015, most people basically gave up on the idea of computing the state root at each block. And that came in the form of what you know as a fast sync, right? You're probably familiar with fast sync. So with the fast sync, essentially, instead of trying to go through blocks starting from Genesis and all the way in computing the state and executing everything and hashing at every block, which is super slow, what we do instead is we're choosing a certain recent block, which we call pivot, and then we download from some peers the pieces of that tree. And once we've done that, we compute the state root on that tree, and then we verify, okay, that matches up with the head. But notice that we have skipped the computation of the root for every other block before that. So since from that on, of course, we start computing the state root for every block.
Mm-hmm. So when we're validating new blocks, we always have to compute the state root.
Again, this is not true. Again, because basically I want to open your mind to other possibilities. Basically, the whole process of discovering TurboGeth is throwing away the dogmas that you might think something has to be true. And the reason why I'm saying is that because in TurboGeth, for example, sometimes we skip the verification of the root. For example, if we sync on hard drive on HDD, it cannot do it for every single block, but it can, for example, do it every 15 blocks, which is, I think, still fine, you know, because if there's some problem, you will notice it anyway after 15 blocks. So I don't see this as a completely dogmatic thing that we have to validate state root after every single block. I mean, depending on what you're doing, you might sometimes skip that. And in fact, a lot of people skip that for most of the blocks when they do fast sync.
Yeah, that's great insight.
Okay, so
then my question is, now we could go. Now we have two different things we can do to optimize it. We can either change the way we store the state completely, or we can store a separate secondary version of the state.
Yeah.
Which would be better?
Okay, so what you just said, the second option, okay, the second option where we start building a secondary structure, which has basically kind of flattish store. This is what I believe currently Go Ethereum is doing. So they also realize that the flat representation has advantages, but they don't want to kind of completely redesign the model, at least for now. So they basically started building this thing on the side, which is the snapshotter. And that's one of the approaches, but from my point of view, maybe that's the only thing they can do. I mean, it depends like what situation you're in. If you want to get the best results, obviously you have to change the data model entirely, because there are a lot of things that you simply cannot do with if you still have the try. I mean,
Yeah.
basically, we're not completely, so thing to understand is that we're not completely throwing away the try as the concept, but we're throwing it away as a physical thing. Where, so essentially another dogma that you have to get rid of is that the try does not have to have a physical embodiment. It could be just a logical concept. And as long as we can produce the state root in some ways which will match up with whatever the try would produce, that's fine. You never have to have a try actually even in memory. And in fact, we used to have a try in memory in TurboGeth at some point, but now we don't even have it anymore as a physical embodiment of that thing. So yeah, you can go like as far as you want. Like you can go baby steps, but then it might take you a long time. Or you can just like rip everything apart and create a new thing. Of course, in our case, we didn't rip. I mean, I didn't rip everything apart. I was discovering lots of things on the way. Like as you probably plan this whiteboarding session is that we're going to start applying optimizations bit by bit, and eventually we'll come to the final design. We could definitely do that if I remember all the steps, but there were a lot of steps.
We could try to directly go to the final design, but then let's talk about problems we have with the, if we would try to implement it right away. So one difficulty I see is that there's one thing that this naive way of storing the try gives us, which is accessing any version of the state.
Right.
So if we have blocks coming on top of arbitrary blocks, and we have to compute state transitions, we need to access every version.
Okay, so this is what I want to question. In order to compute the state transition, you don't need access to all the versions. You only need to access to the previous, well, basically you only need to access to the current version. That's it. You don't.
But which one is current?
Okay, so when you start your state transition, you need to make sure that you are in the correct state, and then you apply the state transition and you change your current state.
So in case of Ethereum, where we have proof of work blocks, does it, like when a new block comes in, does it mean we have to roll back current state a few blocks and then apply blocks from a different chain?
No. Okay. So again, I think what we're kind of missing a bit here is that, again, in naive implementation, you're right. You can think that you can have multiple states at the same time. You can hold on to, because basically you can point to any version of the state by just simply one single pointer, which in your case is the root hash. Yeah, that's fine. So you don't actually have to make a choice. Which one is the current one? You can say, oh, I've got fewer of them around and I can use any of them. If you start using the flat model, you have to make a choice. You have to always know which one is my current state, right? That's my current state. And you can only have one. So now you have to be doing things slightly differently. So if you basically receive multiple blocks, which are on the same height, and you need to make a choice, or you already made a choice, but it was wrong choice, you have to come back and reapply the other thing. So you always have to maintain your chosen state. So you cannot have it like, in multiple ways. So what TurboGeth does, it has only one current state, and it moves it back and forth, mostly only forward. Sometimes it has to move it backwards, but that's not a problem. You move it backwards and then you go forward again if you know the other path is better. And that's another realization you have to do, is that you always have to know what is your current state. Yeah.
So does TurboGeth try to make current state the most recent blocks, or kind of a few blocks back and store diff separately?
The recent blocks. So the current state is always the state that has resulted from whatever last block we have received. Whatever was the best last block received. Yeah. We never try to be a bit behind. We always try to be as far as possible right, in this process.
So then,
And so, okay. And then you probably were asking, how do we go back, right? Is this what your question
I
is?
assume we store diffs.
Yeah. Okay. So that was the case some time ago. We stored the diffs, but actually now we store reverse diffs, which is, there's a slight difference, but it makes a big impact later on. Yes. So we store diffs as we process the blocks. Every time when we process the block, we remember which bits that we have changed, and we obviously, during this execution, we have information about what was the value of the thing, everything before the change and after the change, right? And so obviously the value after the change becomes part of the new state, and the value before the change, this is what we remember, right? And then we remember that for every single block as we go. We call them change sets, and so we have them. And that means that whenever we need to go back, what we simply do is that we take that change set and we apply it to the state, because it will basically just, because it contains the things that were before the change. So essentially it rolls everything back. You can also call them maybe rollback sets or something like that. So they basically allow you to go back. And then you can also go back pretty fast, because, you know, if you want to go back, let's say 3 blocks, you read all these 3 things, you combine them, and you roll back. I mean, you can do it in many different ways, or you can like do merge sort, and because they're already pre-sorted, you can, you know, there's quite a lot of things you can do.
So the flat state is a sorted map, right?
Sorry, what map?
Flat state is a sorted map of keys.
Oh yeah, it's a sorted map. Yes. I mean, it doesn't strictly have to be sorted, but being sorted helps a lot of things along that down the line, because basically having them sorted allows us to do some kind of map reducey things. You know what I mean? Like the basically you can set up this kind of flows of data which have to happen in a certain order. Yeah, it's sorted because basically it's in database, and the database we use is the B tree, and it's sorted. Yeah. Oh, actually, that's interesting. One of the things that haven't happened yet, but let's say that if Etherscan, let's say, or whatever block explorers started using TurboGeth, what they could actually do, I mean, we could introduce the RPC request. So because we actually store the state as the pre-hashed version, let's say before all these hashes applied, so we essentially store it as the mapping of addresses to the values, not the hashes of addresses. What you can also do is that, I don't know how the Etherscan does it. Let's say that you have this, you know, the search bar where you start typing the address, and it shows you the, you know, what are the addresses where this prefix exists in the state, right? Let's say you say type in A, B, C, and it already shows you the, you know, these are the existing accounts with the ABC, and they probably pre-made this specific table. But in our case, you don't have to have a special table because you can simply search through that state. And that kind of helps to be sorted for that case, for that reason.
So you don't hash the addresses?
We do, but we don't hash them until, so basically we only hash them until, we only hash them after we have executed the transaction. So it's all separated. So EVM works on unhashed state. Once it's finished, then we convert unhashed to hashed, and only after that we compute the state root. It's basically a separate process.
But are you worried, like if your backend storage that you use, I assume you use some kind of storage.
That's excellent question. I know what you're going to ask, but it's an excellent question. So why do we store the state twice, right? Once unhashed, one hashed, right? Okay, that's kind of a waste, isn't it? Yes, it is the waste. And it was even more waste when we, so when we actually introduced this extra separation, hashed unhashed. So obviously in the beginning, we only had hash state and we executed AVM on hash state. And that means every time you access something, you have to do another SHA-3 calculation, which is not maybe a big deal, but it's actually would have become a big deal later on. Anyway, so we separated them, you know, and it's obvious the state was 50 gigs or whatever, 50, 60 gigs. So then instead of one table of 50 gigs, now we have two tables of 50 gigs. Bad, isn't it? But it wasn't actually bad, because we also had another table which was more than that, tiny bit more than that, which is pre-images. Remember, I told you about pre-images. So guess what? When we introduced the separated the hash and plain state, we could get rid of pre-images because we didn't need them anymore. Now we have all the plain state. We can run all the queries from a plain state within net pre-images. So essentially, there was no net gain in the storage. Then another thing happened when we managed to squeeze the state into from 50 to 10, then it was actually net positive. We ended up, because we already throw away the pre-images and we wouldn't be able to squish the pre-images that way. So essentially we ended up with 20 gigs instead of 120 gigs. So it is a result of these two operations.
I see. So at that point, could we maybe make kind of go back to go directly to the final implementation? And,
okay. Yeah. So you probably imagine what the final is. This scrollable or for me or not? When I scroll it, do you see it scrolled? Okay.
No.
It's a lag.
Well,
yeah?
well, I'm scrolling it. I'm sorry.
Oh, you're scrolling it.
You can also share your own screen in Zoom if you want, so that I don't share my screen. You want to do it?
This is what. No, but thing is that I no. It's
okay.
Because
Okay. No
I'm basically have an iPad here on my right, and I have a screen here. It will take me a while. Anyway, so but
okay.
If you just scroll it back so to make sure that the past the binary tree, because I'm going to be drawing here. Look, I'm going to be drawing right here. Here, can you see that under the binary tree where I'm drawing? Okay. Yeah, so make it like on the top of the screen or something like this. I'm going to start from there. Okay, so let's say that this is address 1, address 2. Okay. So what basically we do is that we optimize the data layout for EVM, because EVM wants to have instructions like a balance, let's say, and the balance takes the address as an argument, right? And it wants to have a balance. Or if you have essentially a slowed instruction, then it gives you two things. It gives you address and it gives you the location, one, something like this. And it wants you to find a storage item, or if it doesn't exist, it gives you 0. Right. And so that's basically, this is exactly how we map this in a database. So we make it easy. So we map in our database, it's the same table, but we map addresses to the very simple structures, which is basically balance, nonce, something like this, maybe code hash. But we actually want to remove hashes from there as well. But let's say there's some sort of hashes there. Doesn't matter. And the same thing here. Balance, nonce, and some sort of hashes. For these things, of course, we have some kind of concatenation. There is a tiny bit complexity here, which we call incarnation. Incarnation. That's I would say it's an advanced concept. But that's basically how we managed to get around the create to and self-destructions, because that creates a bit of a trouble for a flat model. So essentially for the contract storage, the keys in our database consist of 3 components, not 2. First component is address, 20 bytes. Then there's incarnation, which is currently 8 bytes. And then location is another 32 bytes. Okay, the location is not pre-hashed, and the value is essentially the value, and that's basically the model. So if you want, I can go deeper into what incarnation is, if you really want to know. But do you want to know?
Yes, we do.
Okay. So the incarnation essentially is required because there is some really odd thing about self-destruct and even more odd things about the combination of self-destruct and create too. So self-destruct is this operation. Self-destruct. So what it's very unique operation because what it does, for the very fixed amount of gas, it allows you to delete a lot of data. Theoretically, like if you have a contract which has like million entries, of course it doesn't really happen in practice because such contracts usually don't have self-destruct instructions, but theoretically you can have a really large contract and then with one go you do self-destruct and all that data is gone. It's not visible anymore. And of course if you store everything as this tree model, that's easy, right? You just remove the pointer and everything, and you expect there's some kind of garbage collection will be going on, and then everything which is not referenced by the pointer will be collected, right? That was the thought. But for TurboGeth, because we use the flat model, it means that we can't do this thing. We have to remove it, genuinely remove data. And that wouldn't work because that would be a DOS attack vector if you're requiring to, let's say, for this fixed gas cost, remove a million entries from the database, right? You know, it could take quite a long time. So that's why we decided to get around this problem is to, so first solution would be to just ignore it because we said, okay, we do self-destruct, let's not do anything with the storage. Let's not remove it at all. Okay, fine, because I thought the only way to do self-destruct is first to do create or create a contract using, let's say, a usual transaction to a non-existent address or doing some sort of create. But if you remember how the address of the contract using create is calculated, it calculates from the creators. So it's basically calculated from the creator's address plus nonce and some sort of hash of it. So essentially the idea was that it's theoretical, or it's basically practically not possible using create or this old way of doing things to land the contract on the same address as the previous one. So that's why our strategy of simply not removing the storage worked. We just simply didn't remove it and it was fine until the create 2 came along. And with create 2, it is possible to land the contract on exactly the same address as before. And that is a problem. Like, what do we do with the self-destruct right now? Okay, so that was a big issue. And that's why we started to introduce the incarnation. We still did not want to remove the whole storage straight away, maybe later during the pruning. But so instead of deleting it, we wanted to mask it, to make it invisible. And this is why we introduced incarnation. So every time we create a new contract on the same address, we increment the incarnation. So let's say the first time a contract created on this address, it has incarnation 1. Then if you self-destruct, we still remember that there was something in there. And when you create it again, it gets incarnation 2 and then so forth. So basically then this way we separate the storage items of the different incarnations of the contract, and we don't let them to be mixed up. So that if we basically make them invisible. And then the idea is that when we implement pruning, which we haven't done yet, but it should be pretty easy, we will figure out which incarnations are dead and we just clean them up. But that's how we get around the issue with create 2 using this incarnation thing, which is kind of weird, but it's one of these things that we have to figure out. And incarnation also crucial when you do unwind, because basically, let's say that if we didn't do the incarnations and we did delete all the things, right? Imagine that you did delete everything, self-destruct, but then you said, wait a second, I want to do reorg. Can I just go back and then do the block which did not do the self-destruct. So that means that if you do want to do that in the rework, you have to reinsert all this million things into the database again. So that actually kind of convinced me that we should not never delete them, basically, because you want to go back and you have to reinsert them. And then you might remember, maybe you haven't seen this, but basically I was saying that the self-destruct was probably a bit of a design flaw in the EVM, because it's this kind of operation which could potentially have a very large impact, but has a fixed cost. And then reverse of this operation is even weirder, because I think now, from my point of view, the inverse of any operation should also be quite cheap to execute. But the self-destruct is very weird. Basically, its inverse is even worse than the operation itself.
Okay, makes sense.
So basically, that's the flat model. It says that's it. There's not much more to it.
Just the way you compute the. So
Okay.
let's say we're running the actual node, and now we need to compute the state root.
Okay, state root is computed in 2 steps. So can we scroll it? Can I scroll it, by the way? Let me see. Does it work?
Nope. Nope.
Okay, you scroll it. Okay, so so step 1. Wait, where are you going to scroll it? Okay, under. I wanted to write under the self-destruct thing. Okay, thank you. So first, step 1 is that we obviously need to convert the unhashed to hashed, which is easy, right? It's pretty easy. I mean, it takes a while, but it's easy. So I'm not going to get into the details of that. You can figure that out. So at the end, we are sorry. Okay. So at the end, after the stage, we have address hash at 1 mapping to something, and address hash 2 mapping to something. Okay. To some values. Okay. So then what's next? And the next, you want to compute the Merkle root. Okay. So what we do, so the problematic bit about the flat model is that initially I didn't even bother having some extra data structures for this particular operation, because I would just say, okay, we just recompute this whole thing from scratch all the time. But obviously, I need at that moment the state wasn't that big, and it took about, sometimes it took about half an hour on some devices, but maybe 1 hour on other devices. And so it was okay, but then I thought I'm going to solve it somehow differently. So what we do currently is that it's also not very difficult. So imagine that Radix tree again. Let me see, it's Radix tree. And so what we're going to do in this Radix tree is that we also going to have values here at each point, which are going to be we call them intermediate hashes. So with each node on this Radix tree, let's imagine that we have these intermediate hashes. Okay, so that's basically the meaning of this intermediate hash is essentially it's the hash of that subtree, right? And that's exactly why we like these explicit representation of the Merkle tree, because at any point of time we could let's say that, okay, so let me illustrate this problem. Okay, so let's say that we wanted to modify a bit this bit, right? This bit, okay. So we wanted to modify this bit, and as you know, what will happen is that there will be some sort of ripple effect, right? So if we modify this, then the hash of this whole element will be modified. I'm going to circle it. Then because if this is modified, then the hash of this is modified, right? And then eventually the hash of this is modified, right? But as you can notice is that although so when, let's say, we're computing the hash of the root element, because the other hashes are not modified, we can just use them as they are. And this is exactly where how we basically do the auxiliary structure. So we store the mapping of okay, let me just move it a little bit. It's very simple, actually. It's a key prefix to intermediate hash, and that's basically it. That's the whole magic. So for each node in the tree, we simply store the key prefix mapped to the intermediate hash. That's it. And that structure it turns out to be pretty small. I mean, I think now it's about 2 to 3 gigabytes for the entire state. And that taken into account that it contains all the intermediate hashes for all the basically non-degenerate prefixes. I'm just going to close this. Okay. So basically this is not the magic basically is in the way that we are. So it's not actually, again, this is not the magic. The bit that where you need a lot of interesting engineering is that how do you update the structures and how do you essentially walk through them? Because when we are updating the state root, we start with this change set, which we're talking about, or rollback set, which basically is the enumeration of all the keys that have changed. And then we're starting with the structure, and then we basically walk through the structure, and we carefully, using some sort of hash stack, we just walk through this whole tree and compute the result. So it is a kind of a it requires a careful algorithmic work. It's not like something out of ordinary. So basically, because it's like imagine that you have to do some kind of merge two structures that are already pre-sorted, right? A merge sort, you know. And one way to do it, if you basically do it in memory, then it's easy. But if you, let's say, do merge sort of the two huge files which are pre-sorted, then of course you open two, I would say we call it cursors or whatever. One of them goes through the first file, or iterators go through, and another one goes through the second file, and then just at each point you compare them and you just move them in a lockstep with each other. So the same mechanism here, but what you do is that these two structures. The first structure is this mapping of address hashes to the values, and the second structure is the mapping of the key prefixes to intermediate hashes. Essentially, we have this kind of merge iterator going on through those things.
Cool. So basically, these prefixes are only if there's a node, right? So let's say you have Abba, and then you have like AB is the same, Abacus, right? So then you will have prefix AB.
Yeah, that's true. So yeah, so basically we don't store all the possible prefixes, but only the prefixes that are non-degenerate, that are kind of have something in them. And I guess this is actually this kind of comes to the point is that people before us did not essentially just attempt these things, because I think they should have, because somehow they assumed that all these things will be super hard and it will take a long time. But if they tried, it would be fine, you know. Like, did somebody try before us to just take the entire state and Merkleize it? You know, even for this, like, you know, we tried it, it worked, and then other people start trying it and said, okay, actually that's not that bad. And then and then they started trying other things, like, oh, what happens if when we do this prefix mapping? Oh, actually it turns out to be not that large, you know. You know, if you probably thought it would be like tons of, like, tens of gigabytes. Actually it's a 2 gigabyte or 3 gigabyte. Yeah.
But from the complexity point of view, when you're changing the storage, like you also had to change a bunch of other stuff. Like presumably in this client, it was relying on the fact that every version is available, and now you have to do switches between.
Yes, that's why it took 2.5 years to essentially retrofit all the functionality using this approach, because basically I broke everything. I have to fix it back again, and I just kept breaking it, and until basically this year, around when we did the alpha release in July, I sort of realized that okay, we have unbroken enough, we have fixed enough stuff that has been broken. Yeah, so that's basically the thing that you do. That I did, just broke everything completely and radically, and then try to fix it again.
So what?
Okay.
Go ahead.
Yeah, so the question is like, let's say you need to, from RPC perspective, return some historic state. Is it even possible in Ethereum, or like you don't really need to worry about for this particular implementation?
Good question. Yes, it's a very good question. So there are two ways you can look at the historical state. One is, I think, more important, and one is less important. So you can look at any, so you can ask the questions about, okay, so what was the balance of such and such account at such and such block, right? That's quite easy with a flat structure, right? So you just look at you basically, because if you store the state in a flat structure, you can also state the history in a flat structure. In our case, we store the history as those rollback sets, and then we index them. And that's another story. I think actually the data structure which stores the history is more complex than the data structure that stores the flat state. So it's we're basically making an index over the rollback sets, but we can pretty efficiently figure out which block the certain account has changed around this. Sort of basically, if you're asking what was the balance of such and such account and a block 1 million, then we go through our index and we find, okay, when was this account changed first after the block 1 million, and we use the index to find it. And once we found it, we look at the rollback set. Let's say that it was changed in the block 1,000,015. That was the first time it has changed since 1 million. We then open up the rollback set and we look, okay, what was the value before that? And the value before that was actually the value at the block 1 million. And this is what we do for such queries. It's still much quicker than going through all the trees, right?
Right. And so how you store this index to support this type of lower bound operations?
Okay, so accounts? we have one way stored indexes, but now we're actually going to change it to a different way. So the way we change it is so index is essentially a series of block numbers. So index has one record, well, logically one record per account or per storage item. And imagine that the value is basically the string of block numbers. So and those are the block numbers, all the block numbers where this account has changed its value. And you can pack it in different ways. For example, we currently store them as the actual numbers and when split them into the chunks, but we're now moving most of the indices into the bitmap, roaring bitmap indices. So essentially it's just going to be a bitmap with a certain representation, and it turns out to be even more efficient than these just stored as a sequence. And I think we're going to change that soon to the bitmaps. But even without bitmaps, it works. The index works pretty well. And the index is not actually that large either.
Well, it depends on like how active an account, right? So let's say you talk about Uniswap.
Oh yeah, no. What I mean by not that large, I mean in total for all the accounts in the system. I mean let's say that I just let me find if I can find the latest data. I mean the latest that was in like September.
So okay, so the update on it seems to be like incremental constant time because you only need to like update accounts that were touched in the block.
Correct. Yeah. So updates are
While
incremental.
lookup is just a binary search on the top of this right now. Potentially.
Yeah, lookup is a binary search, and so everything is kind of searchable. We don't do full scans. So yeah, this seems to be quite so it seems to be 19th of August, the latest chart. Okay, so basically I just have a data from 19th of August, how big that index is. For example, from that date, the rollback set, or we call it the change set, we probably should remove it. For accounts, it was it? Okay, for accounts, it was 50 gigabytes. For contract storage, it was 65, 66 gigabytes. And then index on top of that, the index for accounts was 16 gigabytes, and index for storage, it was 40 gigabytes. So that's basically allows you to go back to any account or any storage item in a history reasonably quickly and figure out what the value was. And this is what we use for historical re-execution. So what you can do with TurboGeth is that you can pretty efficiently re-execute all the historical transactions. And my recent test was about 38 hours. I mean, it takes just 38 hours to re-execute everything back using the history. I mean, this is basically where you don't keep updating the current state. You don't actually do any writes. You just basically run through the history and you re-executing everything. And I need this because I want to add some extra indices like for code traces and stuff like that. And I decided instead of just rerunning this whole state calculation, I'm just gonna try to do this historical thing. And that's also quite useful for other analysis that people do. It's very useful to be able to run this through in about a couple of days. You just get through all the historical stuff.
Okay.
Yeah.
That sounds good. I think most of the stuff we understand well.
Okay.
I would probably want to ask Misha, Michael, if they have any follow-up questions on top of what we do that might be unique to us. So one thing we do is like garbage collection, and that seems like might help, especially with indices. So you'll just clean it.
Actually, so the garbage collection is going to be trivial in this case. Because what happens with the rollback sets, for example, because rollback sets are keyed by so the keys are the block numbers. So, and the beauty of the rollback sets is that if you remove the older rollback sets, it does not affect the functionality of the newer ones, because they all they never look back, they always look forward. So if you basically think of history, if you think about history as represented as the Merkle trees, right? In the Merkle trees, the historical references go backwards in history, like they go back, and that's why the garbage collection becomes quite tricky, because as you try to delete something old, you have to first make sure that this old thing is not referenced from something which is still current. So you have to look for that. However, if all your references go always forward, so this is the property of the rollback sets, is that all the references going forward, never back. That's why when you chop something up, it never invalidates anything in the more recent history. So that's why the rollback basically becomes deleting a bunch of records from the database. And for the history indices, it's also quite tricky. Well, you still have to go through every record, but basically you truncate. At most, you essentially delete some records and then you truncate one of the records. You just throw a bunch of numbers out of it. Or if it's a bitmap, you just basically truncate the bitmap. So in all these cases, I think we used to have the pruning implementation, but we just throw it away to rewrite it again. It's pretty trivial. And so that's one of the reasons why we have rollback sets rather than like forward diff sets, because it makes the pruning trivial. or because basically we don't need to run any garbage collection at all.
Right. So Michael wanted to say something.
Yeah, one thing I was interested in that we haven't touched on yet, but you mentioned in your talk, was the concurrency changes that you had made, where you were switching from this. You had parallel streams where each stream was, entirely processing the block, to more like stages where in parallel you were doing all the signature verification and then all the transaction execution, et cetera. And
yeah, that's what we do.
Sort of offhand said in the talk that this made things like 10 times faster. And I was wondering if you had some, more details about why specifically that kind of a change made things faster, and like what the parallelism underneath looks like.
Okay, so there's two reasons why it made things faster. First reason is that if we manage to basically, like, first of all, if you zoom out of this whole, what does the Ethereum client actually do, right? And what it does really is that it receives some new data from the network, right? That ingests new blocks or something, and then it basically goes through the series of data transformation. It transforms this block, transforms the current state. So it's all kind of data transformations until you get to, let's say, to the data in the store history, data in the state, and then you figure out the state root and so forth. So it's basically all data transformation. And so the first realization that first reason why the stage sync is faster is because if you now take this en masse, it's basically at a large scale. If you have to do a lot of transformations, then you can, and all these transformations end up taking stuff from the database, doing something with it, and putting it back into the database. So when you're actually putting stuff back into the database, it matters quite a lot in which order you're putting it in. So if your database is empty, if your table is completely pristine empty, as what happened in the initial sync, if you pre-sort all the data with the sorted level of keys, then inserting in this way is about 10 times faster than if you're trying to insert them in some kind of random order. Essentially, instead of using database as your sorting algorithm, which is basically like it would be some kind of insertion sort, right? Basically on a disk, which is actually a bad idea. Instead, if what we do is that we do quick sort of the memory chunks, then put them into the files and do merge sort out of the files and into the database. And then database doesn't have to do any sorting. It just puts the data in the disk, on the disk. So essentially, we're utilizing much more efficient sorting algorithm to put the data in. And on that large scale, it matters quite a lot. I mean, you would not think of this, but it does matter. The sorting algorithm matters. And that's the first reason. And the second reason is slightly more unexpected, is that when you separate this work into these kind of much more homogeneous stages, and you start looking at them, first of all, your profiling becomes much clearer. You start seeing things that you haven't seen before. You start looking, basically all your bottlenecks become clearer. And then
so now are you literally running, like, is there literally a piece of the code that says, we are currently in stage 1 and we've got some worker threads doing this?
There is a directory in the code which is called ETH stage sync, and then it lists all the stages by the names. It's stage header, stage this. I mean, we don't call them by the numbers because we sometimes insert new ones. But you can see each stage essentially has two functions. One function is move the stage forward, another function move the stage backward when we do the unwinds, and at each point it gives it receives the handle to the database transaction, which is already pre-open, so it needs to do its job, take the data from what it needs to, put the data where it needs to put, and then job done. And then the same happens on the other direction, and at some point the overall kind of driver thing will decide when to commit that transaction. Because, for example, one thing we do is that we don't commit every stage, we just commit in cycles, like when so to make sure that if you're running like a block after block, your database is always consistent up to the like latest block. You never see the state of database in the middle of processing one block. You always see it at the points where, the block is completely processed and committed. And, if you're external reader, that's what you see. You see the very consistent snapshots. And that's actually quite important for, for RPC requests and stuff like this. So you can simplify things quite a lot if you have this assumption. But yeah, the second reason is that, as you can imagine, the code organization becomes different. You have these much clearer chunks of code, which do one thing and do them well. And, you can think about, okay, can I do? So you sort of like, you unleash the creativity a bit more of people who working with this code, because they can now, it's sort of the problem space is much smaller. You can simplify things and you can profile them much better. You can like, oh yeah, like this is the bottleneck. And we had these moments where lots and lots of optimizations actually happen after we have separated stuff out, because it becomes basically obvious. Okay, this is why it's slow, or this is why it's still slow.
Right. Yeah. Yeah. Okay. That makes sense. And then that actually leads us into the last thing that you talked about was the architecture, right? You wanted to do some pretty heavy architecture changes.
Oh yeah, we're already doing this. Yeah.
And like most of on that slide, it hadn't started yet. But do you want to just like talk a little bit about?
Well, actually, if you watch the one that I did last Friday, the 23rd, this is where I went more into detail about the architecture components. But I'm going to shortly explain you what I meant. Is that it started with RPC daemon when we split it up, and we decided to ship TurboGeth as already two components in the beginning. So RPC daemon was already separated. And it's a moment it's running through some gRPC connection. But actually what we will do quite soon, and I mean, it's already working, but we don't advertise it yet. If you still want the sort of the old way of running everything on the same machine through the same database, you can still do that using shared memory. It works. But we as I say, we don't advertise it yet, because we need to fix some other, we need to make sure that migrations happen in exclusive mode, so and so forth. So there's some technical details, but now we have an appetite for more component separations, because actually I think this is important, and I think it would be crucial for this whole project to grow and become stronger. Because I think the sort of the death of other projects, or maybe all certain, like not a death, but a considerable difficulties of other projects were that over time, the development team cannot grow very fast, and so over time the team becomes overburdened by all this feature requests and all this stuff, because it's being pulled into all sorts of different directions, and the core team, which still understands the code, cannot basically satisfy this growing demand on like, oh, we need this, we need that, and we need to fix that, and we need to fix this. So I'm expecting that by splitting things out and actually making other people code owners, let's say one of the good example would be transaction pool. We want to split it out and make other people code owners so that they can run their own releases. They can, so we will have interface, we will agree on the interface, we will run the core part, and they will be running, they will be developing transaction pool, and it will be compatible. And at some point, I think when we fill the functionality gaps, I would like the RPC daemon to also be a separate project run by different people. And then
right. So the idea here is not about scaling, the software itself. It's about scaling the organization around the software.
Exactly.
Right? You want to be able to...
Exactly.
Yeah.
Because what you also, it's only natural that this should happen if we want the system to grow. Like, because okay, of course it becomes more complex for the users to say, okay, now it's got 6 components. It consists of like, what do I do? Like, I need to run a sentry, transaction pool, daemon this, daemon that, like here, like 6 different things. How do they talk to each other? Yeah, that becomes more complex. But like then there will be another tier of people whose job will be to package this all together. Like DAP node, for example, they already made the package of TurboGeth, but I expect them in the future to make packages of selected bits that people want. Like do you want the component with these things, or like the package
Sure.
with
It
these
gives
things,
you
or that thing?
more freedom to customize your node to suit whatever your needs
It's
are.
like it's like a different Linux distributions and stuff like
Yeah.
this. So there are people who are specializing on providing certain distribution with certain flavors, and I think that's kind of a sign of the healthy growth or of the system, where you have different tiers of people doing different things, like not necessarily like core developers doing everything.
Yeah, for sure. Okay, cool. Yeah, I think at Near actually we do have a pretty good separation of components into different modules in the code. Anyways, it all ultimately gets compiled up into the same monolithic binary at the end, but like the code itself is sliced up nicely.
This is actually, if you watch this presentation, I started with the kind of discussion about code ownership and why it is important for the code to be outside of your binary. Even I think it's quite, I mean, for some people it might be just a semantic difference, like semantics, but not. It's
it feels like an implementation detail, right? Like whether or not it's running in the same process. Yeah, but
it's not implementation detail, because it's much more. So basically, I was explaining why it's very hard to like get the changes in some of the implementations, in pretty much all of them, is because people feel ownership. They don't want to just, they need to personally verify a lot of things, like most of the things, to make sure that if something bad is, it's not going to affect the quality of the product, because they're going to be responsible for the result in any case, not the people that, you can't blame the people that you accepted contributions from for all these things.
Yeah, of course.
I mean, you can, but it doesn't really,
doesn't look good. It doesn't grow community very well if you do that.
No, it does not. No, it does not. So you're essentially, but the proper componentization with the proper interfaces, very well defined, documented, sort of stable interfaces. Only these things give you the ability to separate the code ownership, not some kind of kludge inside the code base that you're called a pluggable something like.
Sure. Okay. Yeah, and I guess the other advantage, right, is when you have separate binaries, you can have entirely distinct release cycles, right? Like if you're all compiling up to the same binary, then you're all on the same release schedule. Ultimately, at the end of the day, you cut one release. Who knows what features got in there. Exactly, and then you have to be much more disciplined about the versioning of the interfaces. You can write in different languages, of course, if your interfaces are, and that's actually already happening. As I pointed out in my presentation, we already have two implementations of, they're not production ready, but we have two implementations of P2P sentries, one in Rust, one in Go. We have two implementations of the core execution component, one in Go and one in C++. This whole thing is, we actually probably going to have 2 or 3 implementation of transaction pool, one in Go, one in Rust, and one in in Python. So I think that's cool. This is the future, right?
Cool. Well, thank you so much. I think we're out of time.
Yeah.
Okay. Right. No, it was a pleasure. So I hope that it was useful. And
yeah. Thank you so much. I appreciate it.
All right. Thanks, guys. Bye.